Look at the energy of a crashing ocean wave. It appears to be an unpredictable explosion of water that defies simple measurement. But to a physicist, that rolling water, the sound hitting your ears, and the light entering your eyes follows a strict, predictable order. The challenge is capturing a disturbance that never stops moving. It requires a mathematical language that can describe a physical shape while it travels through space. Take these two overlapping sine waves. At a glance, they might seem identical, but one is slightly taller, and the other starts just a millisecond later. Relying on visual observation alone isn't enough to track these shifts. As the waves travel, those subtle differences in height and position determine how they interact with their environment. To accurately predict a wave's motion, you have to define its two primary traits, its maximum height and its precise timing. This predictive power starts with the mathematical framework used to describe a wave moving through a medium. This is the foundational code for a sinusoidal traveling wave. Each symbol represents a physical property of the motion. First, look at the letter A sitting at the front of the sine function. This is the amplitude. It measures the vertical distance from the resting equilibrium point to the highest point of the crest. Even when the wave dips into a negative trough, the amplitude value remains a positive number. It represents the absolute magnitude of the displacement. The amplitude establishes the physical limit for the wave's energy. It tells us the size of the disturbance, but it does not determine the timing of that disturbance. To find the timing, we have to move past the amplitude and into the bracketed section of the formula. Inside these parentheses is the argument that drives the wave pattern forward through time and space. This entire section is the phase of the wave. The phase operates as a coordinate system. It links a physical position, x, to a specific moment in time, t. As time increases, position x must also increase to keep the phase constant. This causes the physical wave pattern to shift right. There is one final variable in the bracket, the symbol phi. Phi is the initial phase angle. It determines the wave's starting position at the exact moment the clock begins at 0. While amplitude gives us the scale of a wave, the phase provides the necessary context for its speed, direction, and horizontal position. By combining the physical limit of amplitude with the coordinate system of phase, we gain a complete description of the wave. Scientists use these parameters to calibrate equipment. By adjusting mechanical dials, they can isolate a specific signal from a background of noise. We can visualize this as a dashboard. On the left, a slider for amplitude. On the right, a dial for phase. Increasing the amplitude stretches the wave vertically. This changes the intensity of the signal without moving its position in time. Turning the phase dial shifts the entire pattern horizontally. It allows us to move the wave forward or backward without changing its height. Defining these variables allows us to convert sound waves into electrical signals and back again. It is the mathematical blueprint that lets a microphone isolate a single voice and transmit it as a clear signal across a medium.